In this video, we will discuss possible options we have to speed up the training process in multi-layered neural networks. The first type of methods, the so-called adaptive learning rates methods, allow to set separate learning rate for each of the weights and thresholds and also allow to change this parameter during training. The second type of methods, the so-called second-order algorithms, allow to focus their training and their weight adjustment on regions promising the suitable minimum of the energy or error function. The last type of methods are the so-called relaxation methods that avoid the computationally intensive assessment of the gradients and use just discrete approximation for the determination of the new weights. Now for the first type of methods based on adaptive learning rates. So for each of the weights and thresholds, we have now a local parameter. So for weight Wi, we have a local learning rate alpha I. And the weight adjustment delta Wi will then correspond to the negative gradient of the error function, delta capital E by delta Wi, multiplied by the learning rate for the weight Wi, so multiplied by alpha I, and obviously we are looking for the negative gradient, so there will be also the sign minus. So delta of Wi will correspond to the term minus alpha I times delta capital E by delta Wi. In this part of the video, we will show three variants of the main algorithm, of the general algorithm. The first one will be the algorithm designed by Silva and Almeida that allows us to change the parameter values according to the position in the error space. So whenever we want to change the right value for the parameter alpha I, we will consider the position of the parameters in the weight space and according to the gradient of the error function. The next algorithm, called delta bar delta, incorporates a kind of inertia into the adjustment of local parameters alpha I. And the last type of methods that we will show here are the so-called super SAP. SAP comes from self-adapting backpropagation, allows to avoid wrong changes in the parameters alpha I. For all the discussed variants, we will now assume that we are somewhere close to the optimum of the error function. For an n-dimensional weight space, this would mean that we are somewhere in the vicinity of the optimum, either global or at least an acceptable local minimum of the error function. Thus, we can assume that here the error function has a quadratic form, or could be at least approximated by such a function. Then the error function could be expressed as the sum of some constants Cn to the square times the corresponding weight Wi to the square. And what we should add would be the sum over all ij's, where I and j shouldn't be the same ones, of dij times wiwj plus some constant. Then the step in the eth direction should minimize the term ci to the square times wi to the square plus some constant k1 times wi plus a constant k2. And these constants k1 and k2 would depend on the values of the frozen variables for the other directions, for the other dimensions. And Ci would then determine the curvature of the parabola. So in this case, the error function could be approximated by a quadratic function and would have a shape of a ball. Based on the assumed paraboloid shape of the error function, we could thus assume that it is possible to find the local minimum in the vicinity of our current point. In this case, the heuristics for changing the parameter alpha could be to accelerate, so increase the parameter alpha I, if in two successive iterations the sign of the partial derivative has not changed. So this would mean that we are heading towards the local minimum we are considering, and we still didn't miss the point where this gradient would be 0, which would correspond to the wanted minimum. And if we should miss the minimum, this would mean that we actually are farther and have changed the direction of gradient. So if the sign of the two successive directions of the gradient would change, we shall decelerate. So this would mean that we should make the changes, the parameter alpha I, smaller in order to not miss it when going in the opposite direction now towards the previously missed local minimum. So when labeling the partial derivative of the error function with respect to the weight wi at the kth iteration as the gradient at the dimension I of capital E at step chi, and the parameter alpha I at the step at the iteration k, then we can proceed to finding and to deciding how to change the learning rates for further steps. The procedure used to adjust the learning rates shall therefore consider both the current weights but also the weights of the respective gradients at the current iteration and the previous iteration. Hence, in the kth iteration, the value of the learning rate for the next step shall be recomputed for each of the weights by the following formula. So the value for alpha I at the iteration k plus 1 shall correspond to the previous value of alpha I at iteration k times u. So u means that we will increase it, we will take an upper value if the product of the gradient of capital E at iteration k and in dimension I multiplied by the gradient in dimension I of capital E at iteration k minus 1 is bigger than 0. This would mean that we are heading into the same direction for the minimum. If we have already missed the optimum, we shall change the direction and use a little bit smaller learning rates. So if the product of the gradient of capital E at iteration k and in dimension I multiplied by the gradient in dimension I of capital E at the preceding iteration k minus 1 is smaller than 0. So this would mean that the gradient has already changed its direction. Then we shall decrease the steps. So the parameter alpha I at iteration k will be multiplied by d, where d is meant for decrease. The constants u and d shall be set by hand, and u shall be bigger than 1, so we will be increasing, making bigger the values for alpha I, and the value for d shall be smaller than 1, so we will be diminishing the value for the learning rates of the weight wi. Then the weight adjustment formula will correspond to delta at iteration k for wi shall correspond to the negative gradient delta E at iteration k for the particular dimension I, and this will correspond to the new learning rates alpha I at iteration k, and obviously the product of alpha I at iteration k and delta, the gradient in dimension I for capital E at iteration k shall be multiplied by a minus sign. Now we have local learning rates for all the weights and thresholds. So this means that we can better reflect the actual shape of the error function in the weight space. We can also let the learning rates grow according to the actual performance of the network. What lacks suitability is the rates at which the learning rates can grow or decrease. By being close to the appropriate local minimum, the exponential decreasing of the learning parameters is of advantage. So if we know that we missed the local minimum, we can very quickly make the learning rate small and better fit the shape of the error function and find the local optimum we want quicker. In the opposite case, where we are for a too long time heading towards the same direction, we would adjust the learning rates and let it grow during the particular steps. So if we would perform many steps, many adjustments of the weights in the same direction, we would also allow the learning rates to grow quickly. In such a case, the learning rates may become actually so large that we might even not notice that we actually missed the right local minimum. The problems connected with the too quick growing of the learning rates in the algorithm by Silva and Almeida can be remedied by means of another algorithm called delta bar delta. In this technique, the acceleration of the learning rates is done more cautiously than in the previous algorithm. A quick deceleration is quite fine. So for the kth iteration, the delta bar delta algorithm uses the change in local learning rate parameters just by adding a small value. So the growth occurs not exponentially, but in a linear way. For deceleration, we use the exponential decreasing of the learning rates. So for the learning rates for the weight wi, so alpha I at the iteration k plus 1 shall correspond for the same direction for the gradient to alpha I at iteration k plus u. So if the product of delta I, the gradient at dimension I for capital E at iteration k times a delta term, not the gradient directly, but the delta term delta I at iteration k minus 1 is bigger than 0. If the product of the gradient in dimension I at capital E for iteration k times the delta term I at iteration k minus 1 is smaller than 0, then the new learning rates shall be set as alpha I at iteration k times some constant d, and elsewhere we won't do anything. So if it's 0, we will let the learning rates be the same like at the iteration k. So u and d will be some fixed preset constants, and the delta term corresponds or expresses a kind of inertia in considering also previous gradients of the error function. So delta I at iteration k will correspond to the term 1 minus phi, where phi is a constant, times the gradient in dimension I of e at iteration k plus the constant phi times the term delta I at the preceding iteration k minus 1. And the weight updates will then occur without considering the momentum terms. So the change of the weight wi at iteration k will correspond to the negative gradient delta in dimension I of E, capital E at iteration k times alpha I at iteration k. The last technique based on adaptive learning rates that we will discuss here is the so-called SuperSAB algorithm. SAB comes for self-adapting backpropagation. Similarly to the preceding two strategies, it is also an adaptive acceleration strategy for the backpropagation training algorithm. And similarly, like the previous two techniques, if the algorithm goes into the same directions towards the local global minimum that we see as an acceptable one, the pace is increased, so the step and the learning rates are increased. Where this algorithm differs from the previous ones is the choice of the step that is taken in the vicinity of the minimum we would like to achieve. The preceding algorithms took the step towards the foreseen minimum, and if the step was returning back to a missed minimum, then the step was decreased, so the learning rates were decreased. This algorithm tries to make just the right steps. So if it recognizes that the step that it would have to take is a wrong one because of changing the sign of the gradient, this algorithm prefers to not do the step. Instead, it remains in the preceding position and decreases the step and tries again to make it. If the smaller step would still lead to an inverse direction, so if the local minimum would be missed, then again it goes back, stays in the same position, and tries to make an even smaller, shorter step. So by doing just the right steps, this algorithm is relatively stable, of order quicker than the original backpropagation algorithm, and relatively robust against the choice of initial parameters. It uses the momentum. So if a step is taken, the algorithm uses the momentum. This accelerates convergence in flat areas of the weight space. So if the algorithm continues to go into the same direction, it uses the momentum in order to make the steps bigger. On the other hand, in steep areas of the weight surface, the momentum term curbs oscillations that would be caused by changed signs of the gradient. Anyway, if the step taken should be the wrong one, the algorithm prefers to not take this wrong step and rather tries to make the learning rate smaller and then perform a correct step into the right direction towards the wanted minimum. When summarizing the supersub strategy, we will use the following notation. Alpha plus will indicate the multiplicative constant that is used to increase the learning rates. For our purposes, it's enough to set the parameter alpha plus to 1.05. Then we need a multiplicative constant to decrease the learning rates. This constant will be labeled as alpha minus and will be set to 2. To start the strategy and the training, we will use the coefficient alpha start as the initial value for the parameter alpha ij. So each of the weights and thresholds will have its own parameter alpha ij. And at the beginning, this value can be set to alpha start, and the value shall be chosen like 1.2. Then we will use a momentum term, and for the momentum term, we will use the momentum rates alpha m set to 0.3. This entire strategy will be described by the following steps. In step 1, we will set all the local learning rates alpha ij to the initial value alpha start, which we chose to be equal to 1.2. In step 2, we perform the given step for backpropagation with momentum. So we assume that this was the iteration t. In step 3, we will choose whether to increase or decrease the learning rates. So if the derivative, the gradient for the corresponding weight wij goes into the same direction like before, so if it didn't change its sign, then we will increase the learning rates for all the weights wij, because we go still into the same direction and thus we want to make the steps bigger. So the new learning rates alpha ij at iteration t plus 1 will be set to the preceding learning rates alpha ijt, and these will be multiplied by the small multiplicative constant to increase them by alpha plus, which we set to 1.05. In step 4, we shall consider the cases where we just overshoot the weight adjustment and missed the underlying local minimum. So if the derivative of the error function with respect to the particular weight wij changed its sign, then we shall annul the preceding weight change. So we should kind of go back from the wrong step, and in our cases this would mean that we would end up in the point, in the weight point where we started to make the not good change. So we will annul the previous weight change that caused the wrong step and changing the sign of the gradient. So for us, we can implement this step as setting delta wij at iteration t plus 1 equal to minus delta wij at the iteration t. So this was the wrong step. So by doing this, we will annul it. Then we will use smaller learning rates. So we will decrease the applied learning rates. So alpha ij at time t plus 1 shall be chosen as a ratio of the previous learning rates alpha ij at iteration t divided by alpha minus, which was set to the value equal to 2. So we will basically halve the learning rates. And then we will set the delta wij at iteration t+1 equal to 0. So this step, this setting of the weight change equal to 0 occurs here because we are using the weight adjustment with the momentum term. So in order to not make the wrong steps, we shall annul the part of the momentum terms used for adjustment. So in this way, the previous step will be not considered for the next training step that uses the momentum. So it can still use the momentum term, but as the delta change of the weight is set to 0, it won't matter. And the final step 5 is the iterative step. So we, by taking step 5, we will just follow and go to step 2 and iterate further. Both the standard backpropagation training algorithm and its variants based on adaptive learning rates consider just the information regards the gradient to perform a step in weight adjustment. Simply, whenever performing a step, they just look for the steepest gradient descent. The second type of algorithms that might be used for speeding up the training process, the so-called second-order algorithms, take into account more information about the shape of the error function than just the gradient. They consider the curvature of the error function. And in order to consider this type of information, they use a quadratic approximation of the error function capital E. When considering this type of information, they use the Taylor series to approximate the function capital E. When considering the weight vector of the network, W, and the error function capital E for the current point in the weight space W, then the Taylor series approximating the error function capital E at the point in the weight space W plus H plus some step would be approximated by means of capital E at W plus H could be approximated as capital E at the point W plus the gradient of the function capital E and the point W transpose and multiplied by the vector H plus the last term that consists of 1/2 times the H vector transposed times the matrix delta to the square for capital E and the point W times the step vector H. The matrix delta to the square for capital E at the point W is called the Hessian matrix, and its n times n elements represent second-order partial derivatives of the error function with respect to the particular weights. Well, for the second-order algorithms, we have assumed that we are in the vicinity of an acceptable local minimum, and the error function has a quadratic shape in this region. So we can approximate the error function by means of the Taylor expansion and hence at the point W plus H, the value of the error function should correspond to the value of the error function at point W plus the gradient of the error function at the point W transposed times the step H plus the quadratic term 1/2 times the step vector H transposed times the Hessian matrix for W and multiplied by the step vector H. For this point, we could compute the gradient of the error function. So we will basically perform differentiating of the function e at the point w plus h by h. So what we get will be the gradient for the function capital E at the point w plus h transpose that could be expressed as the values for the gradient of capital E at the point w transpose plus the term h transposed times the Hessian matrix at the point w. When performing a step, we obviously would like to perform just one step, just a single step, h, that would yield the ideal results, basically corresponding to a point where we would be directly in the at the minimum of the error function. So when considering this goal, obviously the left-hand side of the equation should be equal to 0. So when performing a step h, that would lead to a 0 gradient. We would be located in the optimum point of the error function. For the expression that we have on this slide, we know that the left-hand side should be equal to 0, and we know the values for the gradient of the error function at the point w. We also would be able to assess the elements of the Hessian matrix, and the only thing that we don't know now would be the step h. So by reordering the right-hand side, we would obtain the equation for computing the step h. So step h would then correspond to the term minus the inverse of the Hessian matrix times the gradient of the error function capital E at the point w. Anyway, this would be in an ideal case where we would be able to determine the inverse Hessian matrix, and that the approximation that we used by means of the Taylor series would be an adequate one. Because this is often a too strong assumption, we may use to find the right point, the optimum, by taking just one step h. We might use the so-called Newton's methods. These methods work iteratively, and the weight adjustment in the kth iteration is performed according to the step we showed in the first half of this slide. And the new weight w at the iteration k plus 1 would correspond to the weight at the previous iteration, the iteration k, minus the inverse Hessian matrix at the point w times the gradient of the error function capital E at the point w in at step k. These algorithms usually converge very quickly. The problems that might be connected with the Newton's methods are referred to the computation of the inverse Hessian matrix. Although the Newton's methods are quite straightforward, their main problem is first the strong assumption of the quadratic form of the error function, and second the computation of the inverse Hessian matrix. For this reason, the so-called pseudo-Newton methods are introduced and used in order to avoid the problems connected with the intensive computation of the Hessian matrix. in our case, the simplified form can include just the computation of the diagonal elements of the Hessian matrix. So we would just compute the second order derivatives of the arrow function capital E at the point W for each respective weight Wi. So the Hessian matrix would just contain the elements delta square of capital E at the point W with respect to delta Wi to the square. The remaining elements would be set to 0. So the weight adjustment would then proceed according to the following formula, where the weight at the iteration k plus 1 for the eth weight would correspond to its previous value Wi at iteration k minus the gradient in the dimension I for capital E at the point W divided by the second order derivative of the function capital E at the point W by Wi to the square. These simpler versions of the original Newton's methods thus do not need any matrix inversion. So a limited computational effort is necessary in order to find the required second order partial derivatives. Pseudo-Newton methods tend to work well when the arrow function has a quadratic form. Otherwise, which is a more usual case, problems might occur since the second order partial derivatives can become small and can lead to extremely large corrections. So for this reason, rather simpler variants of the Newton's methods are used. We will cover here in this video two of them, the so-called quick-prop and the Levenberg-Marquardt algorithm. Both of them contain a kind of simplification, further simplification, not just dealing with the second order derivatives for each particular weight separately, and may contain also some iterative correction form in order to avoid problems that would take place when the assumption for the quadratic form of the arrow function was wrong. The quick-prop algorithm goes with the simplification of the original Newton's methods even beyond the pseudo-Newton methods. It takes into account also the second order information about the shape of the arrow function, but just one-dimensional minimization steps are taken. And furthermore, the information about the curvature of the arrow function is obtained not by computing the second order derivatives, but by approximating these derivatives, second order derivatives, by means of the difference of first order derivatives. So the information about the curvature used in the update direction for the weights is computed just as the difference between the current and the past partial derivatives of the arrow function and the difference in the weights performed. So just taking into account the step that would correspond to this change. So in general, this algorithm uses the second order algorithm, but performs independent optimization steps for each of the weights, and the quadratic one-dimensional approximation of the arrow function is here used instead of the true second order derivatives. At kth iteration of the quick-prop algorithm, the change in the weights corresponds to delta K of Wi. So the new weight Wi K plus 1 shall be computed as taking the previous weight Wik and changing it by delta K Wi. At this point, it is important to note that this weight change occurs in accordance with the actual gradient delta I of the error function capital E at iteration k, and the change of the gradient, where the change of the gradient with respect to the change of the appropriate weights corresponds to an approximation of the second order derivatives. So the delta term for the weight change Wi at iteration k corresponds to the gradient delta I of capital E at iteration k, and this gradient is then divided by the negative approximation of the gradient delta I E at iteration k minus delta E at iteration k minus 1 divided by delta Wi at iteration k minus 1. And by rewriting this term, we get the expression for delta K Wi to be equal to delta Wi at iteration k minus 1 times the gradient in the dimension I of the error function capital E at iteration k divided by the difference, and now there's incorporated the change of the sign, divided by the difference between the gradient at iteration k minus 1 minus the gradient of capital E at iteration k. So at this expression, we already assumed that the error function has been computed at the previous steps, so k minus 1 and k, and that we used the weight difference delta Wi at iteration k minus 1 that we obtained from the previous Quick-Prop step. As to express the weight adjustment rules of Quick-Prop in a more familiar way resembling the formula stated on slide 45, we get here for the adjustment of the weights and delta at iteration k for Wi as the negative ratio between the gradient of the error function at iteration k in dimension I and the approximation of the second order derivative. So for the discrete approximation of the second order derivative, we get here the ratio between the difference in the gradients and the difference in the previous weights, so basically the weight step. So for the denominator in the expression, we get the difference of the gradient in dimension I of capital E at iteration k minus the gradient in dimension E of the error function capital E at iteration k minus 1, and for the difference in the weights we get the term delta k minus 1 for Wi. So we have seen that the denominator of the formula is just a discrete approximation to the second order derivatives in the formula on slide 45. The second order derivative of capital E at W by the derivative of Wi to the square. Therefore, we can summarize that the Quick-Prop is basically a discrete pseudo-Newton method that uses the so-called second step. So the second step is an expression that denotes the discrete approximation of the second order partial derivatives. The other pseudo-Newton method that we will discuss here is the so-called Levenberg-Marquardt algorithm. Its main idea has two components. The first one is that we will try to use a better approximation of the Hessian matrix, not just to replace the diagonal elements by a discrete approximation of the second order derivatives. Still, the approximation might be not the best one. Therefore, this technique is an iterative one, and as a kind of remedy or insurance for suitable behavior, there is incorporated a component resembling the traditional backpropagation algorithm. So, this method is much quicker around the minima of the error function, and it consists of a combination of a gradient and a Newton method. When considering just the gradient, we obviously would have to compute the new weights from the old ones and subtract the gradient of the error function, because we would be heading against the gradient of the error function in order to look for an acceptable local global minimum. Then the second order update rule would have to comprise the, or at least a kind of the approximation for the Hessian matrix or the inverse Hessian matrix. So for the second order update rule, we would have to use some kind of rule stating that the new weights should be computed based on the old ones minus the inverse Hessian matrix multiplied by the gradient of the error function. And what Levenberg-Marquardt algorithm does is that it blends these two approaches together. So the weight adjustment rules have the following form. W at iteration k plus 1 shall be computed based on the previous weights, W at iteration k, minus the inverse matrix of the Hessian matrix plus lambda times the identity multiplied by the gradient of the error function capital E at iteration k. And this can be then expressed in the form as W at iteration k plus 1 shall correspond to the weights at iteration k minus the inverse matrix of H plus lambda I, where H is a Hessian matrix, or its approximation we will use, times the gradient of the error function capital E at iteration k. Now let us look how the Hessian matrix could be approximated by the Levenberg-Marquardt algorithm. The Levenberg-Marquardt algorithm tries to approximate the Hessian matrix more precisely than, for example, the quick-prop algorithm does. Anyway, it still will be just an approximation. In order to make things easier, we will for now consider just one output neuron for the network, and we will now compute how the gradient of the error at the output with respect to the particular weight Wi could be expressed. So for a single output, we would get the value for Gi as the derivative of the error at the output with respect to the weight Wi. And for the weight in the output layer, we would obtain the expression as 2 times y minus d, the actual minus the desired output, times the derivative of the actual output y with respect to the weight Wi. When trying to compute the second order derivatives for all the elements of the Hessian matrix, we would have to compute the value for the second partial derivative of the error E with respect to the weight Wi and with respect to the weight Wj. So having the product for Gi, we would get the expression for the second order derivative elements as 2 times the sum of the gradient of the actual output with respect to the weight Wi multiplied by the gradient, the derivative of the actual output y with respect to the weight Wj. And the second term would correspond to the difference between y and d, and the term corresponding to the second order derivative of the actual output with respect to the weight Wi and to the weight Wj. The first part of the term, that product of the first order derivatives, this wouldn't be too difficult to compute. Actually, we would be doing that already by computing the first order derivatives in the standard backpropagation training algorithm. Yet for the second part, that product between the difference of y minus d and the second order derivative of the actual output with respect to the weights Wi and Wj, this is computationally intensive and very, very difficult. So we will consider the first term for the approximation of the Hessian matrix and will not consider the second one. So for this second element, we will just get some error, but we are fine with that because we shall have there some kind of insurance that if the second order method goes wrong, we still will have there some kind of remedy by means of the standard backpropagation training algorithm. So instead of the real Hessian matrix H, we will use there an approximation just by taking into account the first element, the first term for the computed approximation. So the new weight at time at iteration k plus 1 will correspond to the weights from the previous iteration, wk, minus now the term corresponding to the inverse of h, or its approximation, plus lambda I, multiplied by the gradient of the error function, capital E, at iteration k. You can see that in the brackets we have some parameter lambda. Usually this parameter lambda is set to some positive value, and by setting or tuning the values for lambda, we can prefer more or less the standard backpropagation, or force more the second order approximation to take place. So we can now replace the function h by the product of two Jacobians, basically the product of two gradients for the actual outputs. So the new weight w at iteration k plus 1 shall be computed as the previous weight at iteration k minus the inverse matrix that will be computed as a product of the two Jacobian vectors j at iteration k transposed by and multiplied by j at the iteration k plus lambda times identity, and this matrix, this inverse matrix, shall be then multiplied by the gradient vector for the error function, capital E, at iteration k. So if we are in the vicinity of the optimum weights and the approximation of the Hessian taken as a product of the two Jacobians is good, then also the Gauss-Newton part of the algorithm performs well. Anyway, if we are away from the minimum or in the regions of negative curvature, although the Gauss-Newton approximation wouldn't work well in these regions, we still have there some kind of remedy that corresponds to the part where we take into account the standard backpropagation, the gradient. Well, because we don't have anything better than a simple steepest gradient descent is used here. Thus, the Levenberg-Marquardt method represents a mechanism for varying between the traditional steepest descent and the Gauss-Newton steps that depend on how good the approximation is at the local area. Actually, the control of the role of the Gauss-Newton method and the steepest gradient descent can be chosen by means of setting the parameter lambda. In the weight adjustment rules, you see that the parameter lambda has to be chosen according to the character of the error function in the weight space. When lambda is chosen small, then the step for weight adjustment that we take approximates better the second order Gauss-Newton method and prefers the weight adjustments according to this method. Anyway, if we choose lambda to be bigger, then more or less steepest gradient descent steps are taken. Now the strategy of Levenberg-Marquardt, how to perform the weight adjustments, can be summarized in this slide. So for step 1, we will preset the values for lambda. We can start, for example, with the values equal to 0.001. Then we will compute the new weights according to the Levenberg-Marquardt algorithm. So the new weights at iteration k plus 1 shall be computed from the previous weights wk minus the inverse from the sum of the product of two Jacobians, jk transposed and jk, plus the parameter lambda multiplied by the identity matrix. And this inverse matrix shall be multiplied by the gradient of the error function capital E at iteration k. Basically, the Jacobians correspond here to the gradients of the actual output with respect to the weights. If the error increases, then we shall increase the values for lambda, let's say 10 times. This would mean, namely, that we were wrong with the assessment according to pseudo-Newton. So, therefore, by increasing the value for lambda, we will prefer to readjust the weights more according to the standard backpropagation. Otherwise, this would mean that we were right and the error got smaller. We shall decrease the value for lambda again, let's say 10 times, and shall update the weights. So again, by the formula that we have here, so W at iteration k plus 1 shall be computed based on the previous weights wk minus inverse from the sum of the product of j at iteration k transposed and j at iteration k, and added to the product of lambda identity and multiplied by the gradient of the error function capital E at iteration k, and we shall return go back to step 2 and go further with the adjustment. The last type of methods that we will discuss here for speeding up the training process are the so-called relaxation methods. Sometimes they are called weight perturbation methods. The core idea behind these approaches consists in using just discrete approximations for the gradient. In the same way, like the quick prop used discrete approximation of the second order derivatives and approximated them by the difference of the first order derivatives, here the first order derivatives are approximated by the difference of the error values. So the discrete approximations to the gradient is done at each iteration, and this is done just by comparing the error values for the previous and next weights. So for the initial weights, capital E, W, and for the altered weights, we will denote them as W prime. So for the perturbed weights, we will get the error values equal to capital E for W prime. And the change of the weights, the step beta that is taken from W to W prime is done by means of adding a small value beta to the particular weight Wi or to all the weights. So the weight adjustment is done very simple, and we compute the delta for Wi, so the change of the weight Wi, as the negative ratio between the difference of the error function capital E at point W prime and the error value for capital E at point W, and this will be multiplied by some learning rate alpha and divided by the small perturbation performed beta. This adjustment is then repeated iteratively by randomly selecting the weight to be adapted. The approach taken at slide 55 is rather slow because for each weight adjustment we have to select randomly the particular weight, alter it, and look for the change in the error function, and only afterwards the particular change update is done. An alternative approach providing faster convergence would be to perturb the output of some neuron I, and thus for the actual output OI, we will add some term delta OI. Then we will compute the difference in the error function, the difference between capital E and capital E prime. And if the difference is positive, then the new error could be achieved by using the output of the actual OI plus the added difference, the added perturbation delta OI for the ETH neuron. If we would use the sigmoidal transfer function for our new network, then the desired potential of the neuron I could be determined as using the inverse function, the inverse sigmoid, for the output OI plus delta OI. And for the standard sigmoidal, where we would have to compute the actual outputs as 1 divided by 1 plus e to minus the potential value, we could determine the potential values corresponding to the inverse sigmoid as the logarithm of y, the actual output of the neuron, divided by 1 minus y. So in the case of weight adjustment, when the previous potential value was the sum of weighted inputs Wk times Xk, the new weights could be computed based on the original weights Wk, and if this term would be multiplied by the inverse sigmoidal function, so basically by means of computing the new potential value, divided by the original potential value, we would get the new weights Wk prime as Wk times the inverse function to the sigmoidal for the parameters Oi plus delta Oi divided by the potential for Wk xk. So the weights are basically updated in proportion to their size. So it should hold that Wk prime divided by the potential xi prime corresponds to the ratio of Wk and potential xi. So this inner kind implies some proportional adjustment. Anyway, this proportion keeping can be avoided by means of introducing some stochastic factors or further node perturbations that can be alternated with the weight perturbations.